let's continue. Let me open the table of content first. Okay. We are in chapter 17, and if I remember correctly, we are in section other approach here. Okay, let me open that. Okay, we already take a look at this. The level mechanism. And then okay, this one too. We have to take a look at basic strategies too. Okay, and then let's take a look at other approach. Beyond the basic approach described above, there have been a host of suggested techniques and algorithms to improve memory allocation in some way. We list a few of them here for your consideration. That is to make you think about a little more than just best fit allocation. Okay. Segregate list. Alright. One interesting approach that has been around for some time is the use of segregate list. The basic idea is simple. If a particular application has one or a few popular size requests that it makes, has one or a few popular size requests that it makes, keep a separate list just to manage objects of that size. Oh, interesting. All other requests are forwarded to a more general memory allocator. Okay, interesting. The benefits of such an approach are obvious. By having a chunk of memory dedicated for one particular size of request, fragmentation is much less of a concern. Moreover, allocation and free requests can be solved quite quickly when they are of the right size, as no complicated search of a list is required. Just like any good idea, this approach introduces new compilation into a system as well. For example, how much memory should one dedicate to the pool of memory that serves specialized requests of a given size, as opposed to the general pool. One particular allocator, the SLAP allocator by Uber engineer Jeff Bonwick, which was designed for use in the Solaris kernel, handle this issue in a rather nice way. Oh, interesting. One dedicated to the pool of memory that serves specialized requests of a given size. How much memory? Okay. Dedicate to the pool of memory that serves specialized requests of a given size, as opposed to the general pool, right? Maybe something like the split ratio, how many general pool have and how many this dedicated pool of memory have. Be something like this. Pool of memory, and then we split that into general pool and then dedicated pool. So how much is general pool and how much is dedicated pool? Be something like that. One particular allocator, the SLAP allocator by Uber engineer Jeff Bonwick, which was designed for use in the Solaris kernel, handles this issue in a rather nice way. Specifically, when the kernel boots up, it allocates a number of object keys. When the kernel boots up, allocate a number of object keys for kernel objects that are likely to be requested frequently, such as log, file system inputs, etc. Okay, so there is a case for the kernel object. Okay, interesting. The object cases are its segregate, free list of a given size and serve memory allocation, and free request quickly. When a given case is running low on free space, it requests some slab of memory from a more general memory allocator, the total amount requested being a multiple of the page size and the object in question. Conversely, when the reference count of the object within a given slab go to 0. Right? Conversely, when the reference count of the object within a given slab go to 0, the general allocator can reclaim them from the specialized allocator, which is often done when the VM system needs more memory. What is this VM mean? Is it virtual machine or virtual memory? I mean, again, the abbreviation VM can stand for multiple things, right? I'm assuming in this case it is virtual memory, maybe something like that. Okay, let me read this first and then read the aside here. The slab allocator also goes beyond most segregate list approach by keeping free object on the list in a pre-initialized state. Oh, okay. In pre-initialized state, Bonwick shows that initialization and destruction of data structure is costly. Okay. Is it the same reference? Where is it? Oh, okay. It is the same reference. Alright. By keeping free object in a particular list in their initialized state, the slab allocator to avoid frequent initialization and destruction cycle per object and thus lower overhead noticeably. Okay, this is new for me, I guess, that initialization and destruction of data structure is costly. Okay, alright, let me read this aside. Great engineers are really great. Okay, engineers like Jeff Bonwick will not only write the slab allocator mentioned herein, but also was the lead of an amazing file system, ZFS. Oh, okay. Are the heart of Silicon Valley. Behind almost any great product or technology is a human or a small group of humans who are way above average in their talent, abilities, and dedication. As Mark Zuckerberg of Facebook, or now called Meta, says, someone who is exceptional in their role is not just a little better than someone who is pretty good. They are 100 times better. This is why, still today, one or two people can start a company that changes the face of the world forever. Think Google, Apple, or Facebook. Work hard and you might become such a 100x person as well. 100 times person as well. Failing that, find a way to work with such a person. Find a way to work with such a person. You will learn more in a day than most learn in a month, right? Okay. And then body allocation, because coalescing is critical for an allocator. Some approaches have been designed around making coalescing simple. One good example is found in the binary body allocator. Oh, binary body allocator. Okay. Alright, in such a system, free memory is first conceptually thought of as one big space of size 2 power n here. When a request for memory is made, the search for free space recursively divides free space by 2 until a block that is big enough to accommodate the request is found, and a further split into 2 would result in a space that is too small. Oh, to accommodate the request is found, and a further split into 2 would result in a space that is too small. Okay. So does that mean what is it called? The condition is that when we divide free space by 2, we will what is it called? We will get the location that can accommodate the request, and then if we divide that again, the space need to be small. Yeah, I'm still not sure about this. A further speed. So maybe we only split the space until we found the space big enough to accommodate the request is found, and then stop there. Maybe something like that. Maybe. Okay. At this point, the request block is returned to the user. Here is an example of a 64 kilobyte free space getting defined in the search for a 7 kilobyte block or figure 17.8 page 15. In the example, the leftmost 8 kilobyte block is allocated. The leftmost 8 kilobyte block is allocated as indicated by the darker shade of gray and returned to the user. Note that this scheme can suffer from internal fragmentation. Note that this scheme can suffer from internal fragmentation. Okay. In the example, the leftmost 8 kilobyte block is allocated as indicated by the darker shade of gray and returned to the user. Note that this scheme can suffer from internal fragmentation as you are only allowed to give out power of 2 size block. Oh, so the fragmentation inside the allocated space, maybe something like that. The beauty of body allocation is found in what happens when that block is freed. When returning the 8 kilobyte block to the free list, the allocator checks whether the body 8 kilobyte is free. If so, it calls the 2 block into a 16 kilobyte block. The allocator then checks if the body of the 16 kilobyte block is still free. If so, it calls those 2 blocks. This recursive coalescing process continues up the tree, either restoring the entire free space or stopping when a body is found to be in use. Okay. Is this the first attempt before the patching mechanism here? I mean, I've read a little bit about patching on other blog posts, I guess. It looks like patching, what is it called? Using a fixed size to divide the memory, I guess, instead of a variable size like segmentation did. Yeah, maybe. I'm still not sure. Okay, this is the figure 17. This is the figure 17.8 Example body manage heap. Okay, divide this by 2 and then divide again and then divide again. But because we only need 7 kilobyte block, this 8 kilobyte allocated memory still have 1 kilobyte unused. Maybe something like that. Maybe that's what it means by internal fragmentation. The fragmentation happen in the allocated memory. Something like that. Okay, the reason body allocation works so well is that it is simple to determine the body of a particular block. The reason body allocation works so well is that it is simple to determine the body of a particular block. Okay, how you ask? Think about the address of the block in the free space above. If you think carefully enough, you will see that the address of each body pair only differs by a single bit. Which bit is determined by the level of the body tree. And thus you have a basic idea of how binary body allocation scheme work. Oh, that's why it is called binary body allocation, because we divide the space by 2, maybe something like that. For more detail, as always, see the Wilson survey. Okay. The address of each body pair only differs by a single bit. Which bit is determined by the level in the body tree. Okay. Alright. Other ideas. One major problem with many of the approaches described above is their lack of scaling. Specifically, searching lists can be quite slow. Lack of scaling. Searching lists can be quite slow. Thus, advanced allocator use more complex data structure to address this cause, trading simplicity for performance. Examples include balanced binary tree, split tree, or partially ordered tree. Given that modern systems often have multiple processors and run multi-thread workload, something you will learn about in great detail in the section of the book on concurrency. Right, the second piece here, concurrency. It is not surprising that a lot of effort has been spent making allocator work well on multiprocessor based system. Two wonderful examples are found in Berger et al. This reference and Evans. Okay, check them out for details. Alright, these are but two of the thousands of ideas people have had over time about memory allocators. Read on your own if you are curious. Failing that, read about how the chiplibc allocator work? Oh, okay, interesting. To give you a sense of what the real world is like. Alright, summary. In this chapter, we have discussed the most rudimentary form of memory allocator. Such allocator exists everywhere, linked into every C program you write. Such allocator exists everywhere, linked into every C program you write, as well as in the underlying operating system which is managing memory for its own data structure. As with many systems, there are many trade-offs, right, to be made in building such a system. And the more you know about the exact workload present to an allocator, the more you could do to tune in to work better for that workload. Making a fast, space-efficient, scalable allocator that works well for a broad range of workload remains an ongoing challenge in modern computer system. Okay. The more you know about the exact workload present to an allocator, the more you could do to tune in to work better for that workload. Okay. It is still ongoing challenge. Alright. This is the reference. A scalable memory allocator hoard. A scalable memory allocator for multi-thread application. Berger and Company's excellent allocator for multiprocessor system. Beyond just being a fun paper, also used in practice. Oh, okay. The SLAP allocator, an object caching kernel memory allocator. A cool paper about how to build an allocator for an operating system kernel. An allocator for an operating system kernel, and a great example of how to specialize for particular common object size. Okay. Scalable concurrent malloc implementation for FreeBSD. Oh, a detailed look at how to build a real modern allocator for use in multiprocessor. Okay. How to build a real modern allocator for use in multiprocessor. The gmalloc allocator is in widespread use today within FreeBSD, NetBSD, Mozilla Firefox, and within Facebook. Okay. A fast storage allocator. The common reference for body allocation, random string fact. Knut give credit for the idea not to Knowlton, but to Harry Markowitz, a Nobel Prize-winning economist. Another strange fact: Knut communicates all of his email via a secretary. He doesn't send email himself. Rather, he tells his secretary what email to send. and then the secretary does the work of emailing. Last note fact: he created text. The tool used to typeset this book. It is an amazing piece of software. What is the footnote here? Actually, we use LaTeX, which is based on Lamport addition to text, but close enough. Okay. Understanding glibc-malloc. A deep dive into how glibc-malloc works. Okay. Amazingly detailed and a very cool read. Alright. Dynamic storage allocation, a story and critical review. An excellent and far-reaching survey of many facets of memory allocation. Far too much detail to go into in this tiny chapter. Okay, dynamic storage allocation, a survey and critical review. Alright. Okay, so homebook simulation. Oh, malloc.py. Let's you explore the behavior of a simple free space allocator as described in the chapter. See the README for detail of its basic operation. Okay, let me explore that, I guess. Malloc. Wait, free space. Yeah, only this one. Okay. 200 line. Alright. Oh, we are using class here. Alright. Always the same comment. Okay. Size of space. Header size. Okay. Alright. Okay, the policy is first best and then worst. Alright. And then that list of ordering. Okay. Add R sort, size sort. Okay, size sort plus. And what is add R sort here? And then set sort plus. Okay, size sort negative. Insert front. Okay, insert back. I'm assuming when we free, what is it called? When we free the memory, this is the policy which, what is it called? Which segment the memory should be returned, I guess. So we can return those free memory at the front of the free list, or maybe at the back, or maybe we are, what is it called? We are sorting by the size, like descending or ascending. I am assuming the negative mean here ascending, maybe something like that. And then the plus here is descending from the big size to the small size, maybe something like that. And this one is small to big, maybe, or maybe the opposite. Yeah, I'm still not sure. And then add or sort, this one I don't really know. Yeah, I'm still not sure what this means. Oh, or maybe this means address, not add r. Yeah, maybe this means address. So we are sorting by the address, maybe something like that. Okay, maybe this one. Let's say we have three lists, right? 1, 2, 3, and then we use 2, right? Okay, let's also provide the size. I guess this one is 2 byte, and then this one is 4 byte. Let's say this one is 8 byte, and then we use this one. Free list 2. Yeah, we remove this, right? And then after we free the use memory, we can return that according to this policy. If we are using insert from, maybe we're inserting in this space, maybe insert from, but yeah, I'm still not sure which one is front and which one is back in this case. Is the n here means front, or is this mean front? Okay, I assume front means this one. So maybe something like this. Oh, sorry. Yeah. What is it called? Maybe something like this. We haven't used this previously, but we insert that at the front, right? Using the insert front policy. And then if it is insert back, maybe we will have this. Okay, maybe we will have something like this. We insert the, what is it called? The memory in the back of the list. Maybe something like that. And then size sort. Again, I'm assuming negative in here means ascending. Maybe something like that. size sort negative here, so maybe we are inserting this in the middle, right? Something like this, because we are doing ascending, right? But then what about if we do plus here? Where should this be placed? I mean, do we need change this something like, change the freely something like this, descending, you know, like from 8 byte to 4 byte to 2 byte, maybe something like that. Yeah, I'm still not sure. How are we gonna size sort here? And then the address sort. Yeah, with this address 1, address 2, address 3. We are inserting based on the address, I guess. And let's put question mark here, because again I'm not sure how we insert the returning free space when using size sort plus or even minus here. Okay. Alright, maybe something like this. The return policy, right? Okay, maybe something like this for the return policy. Okay, this does a ridiculous full list. Wait. Info. Let me put this in here. Okay, this does a ridiculous full list coalesce, but that is okay. Okay, ridiculous, huh? Okay. So does that mean we are only coalescing if every space, if every free space block is free, maybe something like that? So not only when a neighboring memory block free, but we need all of the memory block to be free before we do coalescing. Maybe something like that. We will see. Okay, alignment. -1 if no alignment. Okay, alignment, huh? I don't think we are maybe. Okay, -1 or more than 0. Okay, maybe in the readme we will see an explanation. Alignment only that. Align allocated unit to size. Okay, I mean previously I already read some information about alignment. It is maybe something like what is it called? Something like adding a padding so that the size is uniform. Let's say we only have 3 byte, right? And then alignment is 4 byte. So we add a padding of 1 byte to make the size uniform. Maybe something like that. Okay, and then the malloc here. Okay. Yeah, best, worst, or first. Okay. Alright. Perfect match, no split. Okay. Should never get here. That is an interesting error message. Fail to find a spot. Okay. A simple back on and off list. No calls. Append. Okay. Insert. Alright. Yeah. In this case, insert back we means we are inserting in the back appending to the list, right? And then insert front in here means that we are inserting at the beginning of the list. Oh, free list append. Oh, okay. Yeah, we append first and then we sort the list. Okay. Append, sort the list to reverse false. Okay. And then reverse true. So maybe this one is correct. Maybe. Oh no, yeah, I think my interpretation is what is it called? It's not correct. The negative one is reverse here. Okay, so maybe something like this. Not that one, but this one. Okay, this is the, what is it called? ascending and this is the descending, maybe something like that. At least that is what I understand from this code, I guess. Okay, not meant to be an efficient or realistic coalescing. Okay, not meant to be an efficient or realistic coalescing. Alright. Okay, save core. Okay. The lane. Okay. New list append. Interesting. So we are, I think this one. Oh, we are keep, what is it called? We are keep coalescing the neck boring, what is it called? The neck boring free memory, maybe something like that. Okay, but yeah, we going through all the free list here, I assume. Okay, and then there is this. Okay, the option, seed size, base address, header address. Okay, list order. Alright, call list. Okay. Oh, coalesce the free list. Okay, the default we didn't coalesce anything. Okay, number of random ops to generate. Random ops. What is ops in here means? Ops ran. List of ops. Yeah, what is the ops here mean? Free. Okay. Split. Oh. Is op in here means operation, I guess. So we decide how many operation we have, like allocation or the free to memory operation, maybe something like that. Okay, percent of ops that are unlocked. Okay, percentage of allocation operation, maybe something like that. Unlock list. Okay, and from the code it looks like plus mean we allocate the memory, and negative means that we free the memory, at least from this one, I assume. Negative, right? We free the memory. And then compute the answer. Okay. Alright. Maybe on the next session we will read the readme. So I guess that's it for now. Thank you for watching and see you next time. Bye bye.